Anything under static or dynamic condition creates force. Force under static condition, which is known as weight, which is created by the gravitational acceleration, acts towards the center of the earth. And under motion or under a dynamic condition, body gets momentum, and the change in momentum creates force. That is, if you are going to stop a body under motion, there will be a force created, and if the force created is sufficient enough, there will be a deformation. So here in this section we are going to see the simple stresses and strains. Here I am considering about the change in impact of same body under different velocities. If the velocity changes, the momentum changes, and if change in momentum, that means force changes, the deformation also changes. And if I combine both the velocities, then also deformation changes. So the deformation changes when the force applied on the body changes, and force changes when the velocity or the momentum of the body changes. So this happens in the dynamic condition, but also in the static condition deformation happens. So let's take another example for that. So here I am considering about 1000 liters volume of water and placing it on a weak plastic structure. So the internal resistance of the structure won't be enough to withstand that much of weight, so it definitely deforms under the load. So the deformation happens when the force applied on a body increases beyond a limit. So if a body can withstand high amount of force without any deformation, that implies the body is having high value of strength. And also we used to study this kind of strength of materials for designing and manufacturing mechanical components that can withstand high value of force under static and dynamic applications. And while studying about the strength of materials, it is not enough to learn about force. We have to be aware of the size, shape and area where which the force is applied on the body. Leave it about the materials, consider about yourself. If you are very strong mentally and physically, that means you will be having less amount of weakness, and if you are very weak, then you will be having less amount of strength. So if strength increases, weakness decreases, and weakness increases, strength decreases. They are inversely proportional to each other. Same thing happened in the case of materials. And also strength is inversely proportional to the force applied. That is, if I increase the force applied on a body which is having a cross-sectional area A1, then the body starts deform and it will break at a particular load. Then if I increase the area of cross-section of the body, then size of the body increases, so strength increases. Then we can say strength is directly proportional to area, and the body won't deform with increase in force applied. So strength is inversely proportional to the force applied and directly proportional to the area of cross-section of the material. And if you combine both, we can say strength is proportional to area by force applied, and the inverse of strength is called the rate of deformation or weakness or brittleness of the material, and force per unit area is called the stress inside the material, so which is having the unit of Newton per mm square or Newton per meter square. While considering this system, the force applied in a unit small area of the system is considered as the stress, and while multiplying the stress with the area, we will get the total force applied in the system. Unit of the stress is Newton per meter square or Pascal, but for the simplicity we use Newton per mm square instead. and 1 Pascal equals 10 power minus 6 Newton per mm square, because 1 meter equals 10 power 3 or 1000 mm, and we use kilo, mega and gigapascal for the higher quantity of stress. Speaking of deformation, here I am considering a rubber band where which I give a tensile force. Definitely it expands because the internal resistance is not enough to withstand the stress induced. Similarly, the expansion or deformation happens in the case of solid rigid materials, but it would be very small as comparing to the total size. But even though we used to measure the rate of deformation or strain, that is the ratio of change in dimension to the original dimension. Here in the case of tensile force, it will be change in length to the original length. While considering the types of stresses, the collinear opposite forces can induce tensile or compressive stresses. Non-collinear tangential force can induce shear stresses, and shear force along with the moment, that is force multiplied by the distance from the support, can induce bending stresses, and equal and opposite couples or rotational force can induce torsional stresses. Now, for identifying the strength, that is to measure maximum stress that a material can withstand without breaking, we have to do destructive tests like tensile test by means of UTM. By UTM, we can do tensile and compressive tests by giving the crossheads vertical up and down motions. For that, we use hydraulically powered speed control systems, and also it measures the differentially induced stress values by means of perfectly designed gauges. So here we can see the destruction or deformation of material with respect to the force applied, and we can see different stages in deformation like yielding, necking and breaking of material. So we have to understand these different stages of deformation. So at first we have to know about the Hooke's law. That is, under the elastic limit, whenever you apply any force on a material, it deforms, and after removing the force, the material regains its original shape. So we can say whatever the force or stress you give on the material, the strain or the rate of deformation is directly proportional to the stress induced. This is called the Hooke's law. That is, stress proportional to strain, or otherwise stress by strain is a constant under elastic limit or proportional limit, and the constant equals Young's modulus or modulus of elasticity, capital E, if it is tensile or compressive stress, and the constant equals modulus of rigidity, N, if it is shear stress. Both of them are having an unit of Newton per mm square, that is unit of stress, and it will always be constant for particular material. Let's say I am gradually applying force on a ductile or brittle material by means of UTM. So the force is increasing gradually, and till proportional limit, stress will be always proportional to the strain, and if you remove stress at any instant, the material regains its original shape. And here, if you plot a graph between stress and strain, it will be straight. And after the proportional limit till the elastic limit of force, stress won't be proportional to the strain. But if you stop giving the force or stress, the material regains its original shape. So after the elastic limit, yielding happens actually, and that means the material will continuously deform even without increasing load. So there are two yield points, upper and lower points. In upper point, less increase of stress can be measured with a large amount of strain. At lower point, strain will be increasing without increase of stress at all. After the yield point, sudden increase of stress and strain can be measured. So here the maximum stress will be induced. So it is called the ultimate stress. So beyond the ultimate stress point, elongation increases and the load decreases rapidly actually. So here we can find the sudden reduction in area of cross section at the weaker section of the material called necking. So and after that necking happens, it will suddenly break. So ultimate stress is the maximum stress induced in the material. So the complete stages of destruction or deformation are illustrated here. After complete destruction or fracture of the material, the percentage of elongation and the percentage of reduction in area can be calculated for identifying the impact of force or stress on the material. For that, we have to measure the length and area of cross section of the material before and after the destructive testing by means of UTM. And then we can calculate the working stress or safe stress and safe load for the mechanical application of the material. For that, we use factor of safety and load factor, which will be constant for a particular material. For example, the factor of safety of steel is almost equals to 3 always. Here we have to determine the value of deformation under different stresses. So first of all, we can have the formulas of tensile and compressive stress. So here I am considering about a material of uniform cross-sectional area A and total length L under the uniformly distributed load of capital P. So we know that stress is directly proportional to strain under the elastic limit. So stress by strain is equal to Young's modulus. So substituting the value of stress, that is P by A, and strain, that is delta L by L, then Young's modulus will be equal to P by A divided by delta L by L. So while rearranging, we will get PL by A delta L. So then we have to find out the value of deformation here. So delta L can be rearranged into like this, that is delta L equals PL by AE. So this is the standard equation for determining the change in length or deformation under tensile and compressive load. So if the cross sectional area is different, then we have to calculate like we have to calculate the deformation of individual sections and sum up the value for determining the total deformation, total change in length. So here it will be delta L1, delta L is equal to delta L1 plus delta L2 plus delta L3. Here that is delta L is PL by AE. The general formula is substituting here, and then we will get PL1 by A1 E1, PL2 by A2 E2 plus PL3 by A3 E3. So here, if the material of each and every sections are same, then the Young's modulus will be the same. So we can write like PL1 by A1E plus PL2 by A2E plus PL3 by A3E, because the load is constant here, because the same load is equally distributed throughout the section, and the Young's modulus is same because the materials are same. Then P by E can be taken outside and rearrange the equation like this. So this will be this is the general equation for determining the change in length of material under various cross section area. So we can solve the problems based upon this tensile and compressive stress in the next session. So hope you all understand the concept. Thank you.